Hello everyone. In this video, we will be discussing broadcast algorithms. In one of the previous videos, we discussed the clock synchronization. So if you have not watched that video, I would recommend to watch that first because some of the concepts of Lamport timestamps will be coming in this video. So that video is highly appreciated. Let's get started. So broadcasts ensure reliability even in case some messages are lost. What does this mean? We have three ways to have communication. So one is unicast. That means one sender, one receiver. Let's say you are whispering something in your friend's ear, then it will be known as unicast. Then comes the multicast. That means one sender and some let's say k receivers. So let's say you are giving some presentation in front of your 5 friends. Then even though in your classroom 30 students are studying, but you are only telling this message to 5 friends. So it is a multicast. And the third one is broadcast. As the name suggests, it is broad. That means one sender and receivers. That means you are presenting in front of whole class. So these are the three ways of having communication: unicast, multicast and broadcast. In this video, our main focus is on broadcast. So broadcasts ensure reliability even in case some messages are lost. So if you are telling some message in front of 30 students, then even if some students forget the message, at least one or two will be remembering that. And thus, broadcasts ensure reliability. But if each node is broadcasting to every other node, it becomes very expensive with big of n square complexity for n nodes. So let's say there are n students in your class. Consider that. So n students, each student is broadcasting to other n minus 1 students. So first student is broadcasting to n minus 1. Then second student is broadcasting to n minus 1. And this goes on for n students. So if you sum it up, it will become n square minus n, which is of order of n square. Now if students we replace with servers or nodes in a distributed system, the complexity becomes big of n square with n nodes. So each node sends to only k other nodes, because this is a very expensive process, right? You are sending to n minus 1 nodes. This becomes a very heavy and expensive process. So we decide that we choose a subset k. We choose k other nodes and we only broadcast to those k nodes. Generally we keep k to 2 or 3. So every node will be broadcasting to, and now actually it is multicast, so it will be sending to k other nodes. Generally k is 2 or 3. Now what is gossip protocol? When we hear the term gossip, it comes to this picture. So let's say this is you. You heard something or you thought something. You told your 2 friends. Now, these person will also have some friends. So let's say this person tells this person and the other friend told this person. Then this person is a friend of yours as well. So this person again told you this. So this is kind of a gossip, how gossips spread in a room, right? So this same concept has been taken in computer science and known as gossip protocol. So it is used by Cassandra database a lot. So it uses nodes to node communication to achieve broadcast of information. You see, this is kind of a broadcast, right? You are sending the messages and then getting some information back. Not exactly in this diagram, it is a broadcast, but the general idea is that it is to achieve broadcast. Now, consider how gossips spread. Each node picks some nodes randomly. Let's say 2 nodes. We discussed k, right? So k is equals to 2, let's say. And broadcast messages to them. So here k is 2. So you see, you are sending to first person and second person. Then you see this person. They are also sending to this person and this person, right? So k is equals to 2. So in this picture, each node is picking 2 other nodes and broadcasting messages to them. After a few rounds, there is high chance that each node will receive that message, because the information started with you, then it traveled to 2 other friends, then from those friends it traveled to other friends. after certain amount of time, there is a high chance that every node is having that information. So this is the concept of gossip protocol. So now Cassandra uses gossip protocol because it does not require a centralized coordination service or orchestration service, and hence less infrastructure and overhead is needed. To know if a node is down, each node keeps broadcasting its heartbeat. Heartbeat is nothing but is alive message. That it is basically a small signal to other nodes that I am available, I am alive, I can take the traffic, I can handle the load. So each node keeps broadcasting its heartbeat is alive message. If all nodes gossip that none of them received the heartbeat within certain timeout, then that node is considered dead. So if we ask the other n-1 nodes, did you receive the heartbeat from first server? Let's say within a timeout of 100 seconds. And each node says that no, I did not receive any heartbeat message from first server. That means there is something wrong with first server. Either its network is failed or the server itself is down, and we consider the first server as dead. Gossip protocol does not guarantee ordering of messages. For that we need to use timestamps or vector clocks. So this is where the previous video which I just mentioned at the start of the this video comes into picture. So if you have not watched that video, I would suggest watching that. That video link is appearing now on the screen. Please go ahead and watch that first. So gossip protocol does not guarantee any ordering of messages. Just like you told your friends two things, let's say that I like mango and I like orange. These two messages can travel in any order. First friend can receive M1 then M2, or the second friend can receive M2 and then M1. There is no guarantee. So similarly in gossip protocol, there is no ordering guarantee of messages. So how do we guarantee the ordering of messages? Consider the importance of this fact that you are using Instagram Messenger or WhatsApp. Suppose there is a group of 10 friends. If someone is sending any message, in what order the other person should be receiving? Let's say there are 3 persons in a group, A, B and C. Let's say Amit, Bhavna, and let's say Champak. So 3 persons are there in a WhatsApp group. Now Amit is sending that, hey, I bought movie ticket. The show is tomorrow 7 p.m. And let's say Bhavna received this like, the show is tomorrow 7 p.m. Hey, I bought the movie tickets. Will it make sense to her? The answer is no. So in what order should the messages be delivered to other person in a group? And that's why the importance of this video lies in the Instagram or WhatsApp, any messaging platform. So let's come to the ordering of messages. Gossip protocol does not guarantee ordering of messages. We just saw here. So now there are different types of broadcast which ensure that in what order should we guarantee the messages. So first is FIFO, first in first out. So messages sent by the same node must be delivered in the same order they were sent. So consider these 3 persons as nodes. Now if Amit is sending that, hey, I bought the movie tickets tomorrow 7 p.m. The second message is, let's go out. Then Bhavna and Champak should receive the same messages in the same order in which Amit sent them. So Bhavna and Champak each will receive the message first that, hey, I bought the movie ticket 7 p.m. tomorrow. Second one will be, let's go out tomorrow. So messages sent by different nodes can be delivered in any order. So let's say Amit is sending some messages M1, M2, and Bhavna in the meanwhile is sending M3. So you see that M1 was being sent, in the middle M3 was sent, and then M2. The FIFO broadcast is only considered on the same node. So that means the valid orders of delivery become M1, M3, M2 or M1, M2, M3. Basically Amit is sending M1 and M3 and Bhavna is sending M2. Now you see M1 is always coming before M3, and that's the guarantee provided by FIFO broadcast. So below image are valid FIFO broadcast since M1 is always delivered before M3. So this is Amit, this is Bhavna, this is Champak. Amit is sending message 1. So it is sending to itself, then sending to B, and then sending to Champak. Then in the meanwhile, Bhavna is sending message M2 to Amit, to herself and then to Champak. Then Amit is sending message 3 to itself, to Bhavna and to Champak. So valid orders will be M1, M2, M3 or M1, M3, M2. Or since M1 and M3 are related, but M2 is being sent by Bhavna, so M2 can come before as well. So these are the 3 valid orders in FIFO broadcast. So you got the point? FIFO is concerned by the messages from the same person. It only says that whatever messages are sent by a same person, those will be delivered in the order they were sent. It is not concerned with other persons. So M2 can come before M1, M3, or it can come after M1, M3, or it can come between M1 and M3. But M1 will always come before M3. This is the guarantee by FIFO broadcast. Let's come to the second type of broadcast, which is causal. Causal is a term derived from the term cause. Everything is caused by something. So we say that what is the cause of this? What led to this thing? So causally related messages must be delivered in causal order, the order in which they were caused. So for example, if Amit sent that, hey, I have booked the movie tickets tomorrow 7 p.m. And then Bhavna responds, wow, that's a great decision. So if the message to, let's say Champak's screen looks like this. First is Bhavna saying, wow, that's a great decision. And then Amit's message appears that, hey, I have booked a ticket tomorrow 7 p.m. Will it make any sense to Champak? Tell honestly. Bhavna is responding to a message by Amit. Because Amit said that he booked the tickets tomorrow 7 p.m. That's why Bhavna is complimenting him that that's a great decision. So Bhavna's message is directly caused by Amit's message, and hence to anyone, let's say Champak's example, first Amit's message should come, then Bhavna's, and this is the causal relationship between Amit and Bhavna's message. So Amit's message is the cause for Bhavna's message. So Amit's message should appear before Bhavna's message on Champak's device as well as Amit's and Bhavna's devices. Concurrent messages can be delivered in any order. Concurrent means any messages which are not causally dependent. For example, Amit is saying, tomorrow I have booked the movie ticket 7 p.m. and Bhavna is complimenting him that that's a great decision. In the meanwhile, Champak is saying that, hey, did you do the homework? Now, Champak is not relied on the Amit's message. He might not even have received that. So Champak's message is causally independent of Amit's message or Bhavna's message, and this is known as concurrent message, which is not causally related to any other message. Consider this. In the below image, M2 and M3 are concurrent and not causally related. Hence the valid orders are M1, M2, M3 or M1, M3, M2. So this is M1. It is being broadcasted by Amit. This is M2, which is broadcasted by Bhavna. And this is M3, again broadcasted by Amit to Bhavna and Champak. You see that M2 and M3 are concurrent. They are not causally related. So the valid order will be M1, M2 or M3 or M1, M3, M2. Why not M2 before M1 and M3? Because M2 is closely related to M1. M2 is a response from Bhavna to Amit's message that he booked the ticket for 7 p.m. So M1 will always come before M2. So this is the guarantee put by Causal Broadcast that causally related message will always be delivered in the order in which they were caused. So the first type, FIFO, is concerned with one person, but you see causal is related to multiple folks, how they are related, how their messages are related to each other. Either they are causally related or they are concurrent messages. Now the third one and the last one is total order broadcast, also known as atomic broadcast. This basically ensures that all messages are delivered to all the participants of distributed system in the same order. The first type, FIFO, and the second type, causal, do not guarantee that Amit's, Bhavna's and Champak's message orders will be same. They only guarantee that on each device, the message order will be compliant. So let's say in the FIFO, let's consider the example that on Amit's screen M1, M2, M3 is there. On Bhavna's screen, M1, M3, M2 is there. On Champak's screen, M2, M1, M3 is there. All are valid. Similarly, in Causal, let's say Amit's screen and Bhavna's screen show M1, M2, M3, but Champak's screen shows M1, M3, M2. This is also valid. But total order broadcast says that all three views for Amit, Bhavna and Champak will be the same. The order will be the same. So it is either M1, M2, M3, or let's say M1, M3, M2, or anything M2, M1, M3, or anything, but this order will be same on all the devices. So if we say order must be M1, M2, M3, then below image is valid since all the three nodes received messages in the order M1, M2, M3. So let's take example of Amit. He received the M1 first, then he received M2, then he received M3. So his order is M1, M2, M3. Now let's take example of Bhavna. She received M1 first, then she received M2, then she received M3. So her order is also M1, M2, M3. Now let's take example of Champak. He received M1, then M2, then M3. So his order is also M1, M2, M3. So you see the views of all the devices Amit, Bhavna and Champak is the same M1, M2, M3. So the summary tells us that we discussed three types of broadcast: FIFO, Causal and total order broadcast. Let's come to their formal definitions. If M1 and M2 are broadcast by the same node and broadcast of M1 led to broadcast of M2, then M1 must be delivered before M2. This is the guarantee by FIFO broadcast. Causal broadcast tells us that if broadcast of M1 led to broadcast of M2, then M1 must be delivered before M2. Total order broadcast says that if M1 is delivered before M2 on one node, then M1 must be delivered before M2 on all the nodes. So which one is the most stricter one among these three? Tell me in the comment section and I will review each one comment. Let's come to some of the approaches of achieving these types of broadcast. So some of the approaches for achieving it are single leader approach, where leader broadcast messages acting as a sequencer, but it is a single point of failure. So if there is a single leader, then this leader is the determinant of what orders will be there on each of the nodes. But it is a single point of failure. If this leader fails, then we don't have any backup. The second point is Lamport's clocks approach by attaching Lamport timestamp to every message. This we have already discussed in one of the previous videos. You can see the link now on the screen. Click on that and understand what a Lamport's clock means. So this is the second approach. So in this video, we discussed the difference between Unicast, Multicast and Broadcast. We discussed what a gossip protocol is. We took some of the real life examples and how Cassandra uses this. Then we understand the importance of ordering of messages in systems like WhatsApp and Instagram Messenger. Then we discussed three types of broadcast: FIFO, Causal and total order broadcast, also known as atomic broadcast. And then we discussed what are the approaches for achieving it. There we discussed the single leader approach or attaching the Lamport timestamps. So that's all for this video. If you like the video, please consider sharing and subscribing to the channel. If you have any topic in mind, please feel free to comment and then I will take a look at the topic and will try to make a video on this. Thank you so much.